Good evening everyone. So this is the 7th problem solving session for the NPTEL course Aircraft Propulsion. To introduce myself again, I am Anindo, a PhD candidate and a Prime Minister Research Fellow from Aerospace Engineering Department at IISc Bangalore. And I have conducted 6 live problem solving sessions for the course. We have done with 50% of the course, and we are left with 6 more such sessions including this one. Today we'll be dealing with thermodynamic analysis of aircraft engines, is related to turbojets, turbofans and ramjets, and also look into some um, general aims theoretical question based on this type of aircraft engines. Okay, so in the last class we have seen how we saw how we solve problems on real cycle analysis, and also looked into that when we move to analysis of thermodynamic analysis for jet propulsion cycles or Brayton cycle based aircraft engines, we need to also consider one real effect pertaining to the intake, which is a diffuser, and we can take and we have seen how we take into account the intake isentropic efficiency and use that to compute the total pressure given the ambient conditions. We have seen how we compute the total pressure at the inlet of the compressor. Okay, and so today we'll today start with seeing some problems on nozzles and how we compute the what is what is the significance of the term isentropic efficiency of the nozzle, and how that is defined and everything. Okay. So first we have this is a problem related to nozzle. So it says that air at 200 kilopascal and 950 Kelvin enters an adiabatic nozzle with a low velocity and discharge at a pressure of 8 kilopascal. If the isentropic efficiency is 92%, determine the maximum possible exit velocity. We have to compute the exit temperature and actual exit velocity, assuming constant specific heats for air. Okay, so let me draw the schematic. So we have a nozzle. Okay, so I'm representing the inlet state here as 4, because in general if you see the turbojet engines, 4 is the station number that we generally use to denote the entry to the nozzle. Okay, so 1 is entry to the compressor, 2 is exit of compressor inlet of combustion chamber, 3 is exit of combustion chamber and entry of the turbine, and 4 is the exit of the turbine and entry of the nozzle. Okay, so I'm denoting it here as 4 for it will be easy to relate it to the when we'll do problems on full aircraft engine thermodynamic analysis. Okay, and so exit state is 5. Okay, so it says that this we have seen that this velocity c4 is negligible. It says a very low velocity. Okay, so you can assume that c4 is 0, which means that the total pressure is equal to the static pressure, which is equal to 200 kilopascal, and the total temperature will be equal to the static temperature 950 Kelvin. Okay, this is because our the velocity at the entry of the nozzle is very low, so we can assume it to be 0. Okay, so and we have at the exit we have the static pressure of 80 kilopascal. Okay, and the nozzle isentropic efficiency is given as 92%, 0.92. Okay, so first question is what is the maximum possible exit velocity. Okay, so let us draw the TS diagram. Okay, first. Okay, so since this is an adiabatic nozzle, okay, that means there is no nozzles are generally adiabatic because there is no heat transfer happening, and also there is no work transfer obviously. So the total temperature stays constant. Okay, so T05 will be equal to T04. Okay, so in nozzles and diffuser total temperature stays constant. This you should remember, because of this by energy balance, there is no heat transfer or happening or work transfer, so the total temperature stays constant. Okay, so let's say this is our total temperature to start with. Okay, and let me draw the seeing. So this is, let's say this is our P04, okay, right? So let me draw, let's say this is my P5, okay, all right. So if the this is a 04 state, okay, this is a state 5s. So 5s is the state if we assume that the through the nozzle the flow is isentropic, okay. So it will get expanded to this stage, and okay, and this will be like our, and the T04 will be also equal to T05, and this we can say this is our C5s square by 2cp, okay. Okay, so this is our, this will be the velocity equivalent of the velocity or the dynamic component of our total temperature, okay. So this will, okay, and but when we have actually the process is non-isentropic, it will follow a path like this, okay, and reach here, which is 5, okay. So now we here the if we now project it back here, so this will be our state 05, okay. Now here, and here you see, because the total temperature has to stay constant, okay. So 05 state will be this, okay, and this will be our pressure P05, okay, and this vertical this part will be our the velocity square by 2cp. So this is C5 square by 2cp, okay. So we have seen that these are the, like, if you see these two vertical temperature differences, this first denoted by this orange line and the green line, we can conclude here that the C5 is actually, C5s is actually greater than C5, okay. C5s is greater than C5, okay, which means that maximum velocity is attained if for isentropic flow, okay. So if the flow is isentropic, this, it will follow this orange line, okay, to 5s, and this 04 state will be same as 05s, okay. And so this difference will be temperature difference denoted by this vertical orange bar, that will be your proportional to your velocity, okay. And similarly, if we have the non-isentropic process, which is the green one, okay, so this is our non-isentropic process, the green one, then we go to a state 5, and 05 will be like this. We can see the, again from the temperature, this T04 is equal to T05, okay. And then, and this, now the green vertical gap, that is corresponding to C5, okay. So you can see there, here, from here, that the maximum possible exit velocity is attained when the nozzle operates under isentropic condition. That is, the flow is isentropic, okay. So remember that in case of nozzle, the basic operating principle of nozzle is again is to increase the flow velocity at the exit, okay. So just now correlate this with the thrust equation. So remember, in the thrust equation, thrust is proportional to the difference between the nozzle exit velocity minus the flight speed or the aircraft velocity, okay. So higher the nozzle velocity the thrust will also get a higher thrust, okay. So like, it is ideal that we should, like, it's, so the maximum possible exit velocity in that case for the nozzle can be achieved if we operate the nozzle under isentropic condition, but it is really not possible. So we should try to keep the flow as close to isentropic as possible, okay. So the first part of the question, we have to see the maximum possible exit velocity. So maximum so this is the velocity at exit if flow is isentropic, okay. So let's do that. So this is, again, what we do is your we can just do energy balance, okay. So this is like what should be T, we know T04 is equal to T05. All this comes from here, that H4 plus C4 square by 2, sorry, C4 square by 2 is equal to H5. Okay, let me just start from the energy balance. So H4 plus C4 square by 2 Cp is equal to H5 plus C5 square by 2 Cp. Okay, so now C4 is approximately equal to 0, so this is basically, we can write H4 is equal to H5 minus C5 square by 2 Cp. Okay, okay, I'm writing this as H04. Okay, so this is like showing the stagnation enthalpy. So Cp T04 is equal to T5 minus C5 square by 2 Cp. So okay, so now, so basically C5 will be equal to square root of 2 Cp T04 minus T5. Okay, so now if flow is isentropic, that is the condition when we will attain the maximum velocity, exit velocity, right? So T5 is basically equal to a T5s. Okay, that if you refer to the previous TS diagram, so it will reach the state 5s if the flow is isentropic, right? So basically what we want, so this will be like C5 max, or like you can say right, like, yeah, C5 max is equal to C5 when the flow is isentropic, C5s equal to 2 times Cp T04 minus T5s. Alright, now how we have to find out T5s first. Okay, now since the process is isentropic, we can apply the isentropic relation. T5s by T04 is equal to P5 by P04 whole to the power gamma minus 1 by gamma. Okay, so P5 is our 80 kilopascal and P04 is equal to P4, which is 200 kilopascal. So this is 1.4 minus 1 by 1.4. So from this, T5s is equal to 950, T04 is 950 times 80 by 200 into 1.4 minus 1 by 1.4. So we'll get T5s as 731.2 Kelvin. Okay, so now we put it back there. So then C5 max or C5s is equal to 2 times Cp is 1005 times T04 is 950 and this is 731.2. Okay, so we'll get this C5 max as 663.2 meter per second. Okay, so this is the maximum possible exit velocity which we are attaining when we are operating the nozzle at isentropic condition. Okay, so this is also clear from this TS diagram. Okay, this okay, now second question is what is the so this is done, so this is part A. So part B is the what is the exit temperature. Okay, so this is the means that this is looking for the actual exit temperature. Okay, which is T5. Okay, so this state point 4 is fine, right? This state point 4, this state point 04. Okay, so we have temperature second, just second, just hello, just a minute. 974521 521. Yeah, keep it in the reception. Okay, yeah, thank you. Yeah, okay, sorry about that. Okay, so you was asked me to explain the TS diagram, right? So yeah, so this orange point is clear, right? So this is our inlet state point, inlet stagnation state point. So we have T04 here and the pressure of P04. Okay. So now if we have isentropic process, isentropic expansion through the nozzle. Okay. So now at the exit we will reach this state. Now this is the state I am representing as 5s. So this is a static state. Okay. So this is the static state 5s, and the stagnation state corresponding to 5s will also be the same, this orange point, because the stagnation temperature at both 5 and 4 is same. T04 is equal to T05. Okay, so this is same. So the temperature difference between these 0.04 or 0.5s and this 5s. Okay, so this is this will be is equal to C5s square by 2cp. Okay, the velocity square by 2cp. Okay, so this so you can see that when the process is isentropic, our velocity attained at the exit is proportional to this orange vertical orange line. Okay, okay, this is what I have noted here, this c5 square by s square by 2cp. Okay, so now but when the process is non-isentropic, so it will the process diagram will follow a curve like this, green one. Okay, from 04 to 5. Okay, so this is the actual static static exit condition. Okay, now the for this state point 5, the corresponding stagnation state will be 0.5. Okay, but here also we have to maintain that the T04 should be equal to T05. Okay, T04 is equal to T05s equal to T05. Okay, so the stagnation temperature stays constant even whether the process is non-isentropic or isentropic. Okay, so here you can also see that the T04 is equal to T05. Okay, and so this is the stagnation state, and so the temperature difference T05 minus T5, that should be equal to C5 square by 2cp. Okay, this one, right? So this, now you can see that if you compare C5 square by 2cp and C5s square by 2cp, so you can see this orange vertical line, that difference is higher. Okay, so from that we can say that the exit velocity will be higher when the process is isentropic, or the flow is isentropic. Okay, so that is our C5s. Okay, so the first question was, so this is what is the TS diagram explains. All right, is clear? Okay, now when the question is what is the maximum possible exit velocity, which means that maximum exit velocity can be attained when the flow is isentropic. Okay, so that's why in the first part we computed what will be the exit velocity if the process is isentropic, right? So now, so in general from the energy balance we can see that the expression for exit velocity is given by 2cp square root of 2cp times the temperature difference, the stagnation temperature at inlet minus the static temperature at exit. Okay, so this is the expression for the velocity at nozzle exit. Okay, so when we are saying we have to find out the maximum possible exit velocity, which means that the flow will be isentropic and our exit temperature will be equal to the T5s. Okay, or the temperature attained if the process is isentropic at the end. And if the process is isentropic, we can use the isentropic relation with the pressure ratio to compute the static temperature at nozzle exit. Okay, this one, and then put in the values to compute the maximum possible exit velocity. Okay, all right, so this is the first part. Okay, next part, I hope this is clear now. Okay, but just get used to seeing like distinguishing between the stagnation state and static state, and the when you and just and note that the temperature difference between the stagnation temperature minus static temperature will give you the velocity square by 2cp, that term, or that or the velocity is like proportional to square root of the temperature difference. Okay. Alright, so next part you have to find out the exit temperature. So this is the actual exit temperature. So T5, which is the actual exit temperature, assuming that the, like, considering the actual flow, which is the non-isentropic flow. Okay, so for that we have to invoke the definition of you're talking about this equation. Yeah, so you see this is coming from energy balance. So this is energy balance. So what you have written, enthalpy plus kinetic energy, enthalpy plus kinetic energy. Okay, so now this enthalpy plus kinetic energy is equal to the stagnation enthalpy, right? 804. That's what I have written here. So, and this is and then we represent it like this. Okay, you can also write it, so you can also, so that's how it comes. Yeah, T04 is equal to T05. Yeah, right. Yeah, that's what is come. So if you, so like if you, in this case, if you write this in the on the right hand side, if you write this as, this is also, this is equal to your 805. Okay, so that will give you T04 is equal to T05. Okay, but we need to find out the kinetic energy, so we are keeping it in this form. Sorry, we need to find out the exit velocity, so we are keeping it in like static plus kinetic energy part. Okay, and then okay, sorry, one mistake here. It should be CPT05 by one more. Yeah, right, now it is all right. Okay, so H4 plus kinetic energy plus A equals to H5 plus kinetic energy at the exit. Okay, then on the left hand side we write the entire thing as the stagnation enthalpy, and on the right hand side we keep it as it is, and then replace the enthalpy as Cp times the temperature. Stagnation enthalpy becomes Cp times the stagnation temperature, and on the right hand side we have Cp times the static temperature at exit minus the C5 square by 2. Okay, so now if we rearrange, C5 we will get square root of 2 Cp times the difference between the stagnation and static temperature. Okay, so now again, so when we are asked to find out the velocity when the flow is isentropic, we have to use the static temperature at the considering the flow is isentropic at the end. All right, so we invoke the isentropic relation, find out the temperature at the exit, put it in the in here, and find the exit velocity. Okay, so these are maximum possible exit velocity. Okay, so next part you have to find out the actual temperature. So actual temperature is when the exit temperature is when the nozzle is in, like, actually nozzle is in, the flow is non-isentropic. Okay, so there you have to use the definition for nozzle isentropic efficiency. Okay, which is defined as the actual rise in kinetic energy divided by isentropic rise in kinetic energy. Okay, all right, so okay, so what is our actual rise in kinetic energy? So actual rise is C5 square by 2 Cp, right? So this is, sorry, actual rise is C5 square by 2, and isentropic rise is C5a square by 2, right? Clear? Okay, right, so this is the actual rise. When the actual rise is, actual velocity is C5, but if the flow is isentropic it will be C5s, that we computed. Okay, so now if you go back to the this TS diagram, you can see that this in this this C5a square by 2 and C5 square by 2, that is equal to 2 times the temperature difference, that is equal to Cp, this is equal to Cp times C04 minus C5, T04 minus C5, or Cp T04 minus T5s. all right, so we like can denote the nozzle isentropic efficiency in terms of the temperature difference. Okay, so this is right? So this is again like seeing in the this or so what we are doing is this green vertical line, that length of this green vertical line, and divided by the length of this orange vertical line, right? So that is the our temperature difference, stagnation minus static. Okay. Okay, so this is our gives our nozzle definition for our nozzle isentropic efficiency. Okay. 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 Second. All right. So now, so our nozzle isentropic efficiency is our T04 minus T5 divided by T04 minus T5s. So our nozzle isentropic efficiency is 0.92, T04 is 950, T5 is unknown, T04 is 950, T5s is what we computed, that was 731.2. That is the static temperature at the nozzle exit if the flow through the nozzle is isentropic. Okay, so if you now solve this, we'll get T5 as T5 will be greater than T5s or lower than T5s. So we'll put so T5 is greater than T5s or less than. Yeah, anyone? And just tell me seeing this diagram. So the green point is this is so this is your T5, right? And this orange, this is your 5s. So which is greater, T5 or T5s? Right. So T5 is greater, right? So ideally this value of T5 should come as should be greater than 731.2. So T5s is 731.2, right? So if you solve, you will get T5 as 748 Kelvin. Okay. So as we draw the diagram, we say that nozzle exit temperature is actually higher than the actual nozzle exit temperature is higher than that will be attained in the non-isentropic case. Okay. All right. So next is part C. So part C is the actual exit velocity of air. So actual exit velocity, okay, so actual exit, so velocity formula for velocity is this one, square root of 2 cp times the stagnation temperature minus static temperature, right? So this is 2 cp times T04 minus T5, right? So this is 2 into 1005 into T04 is 950 and T5 is what we got, 748. Okay, so you can obviously see that since T5 is higher than T5s, this temperature difference will be lower and actual exit velocity C5 will get as 637 meter per second. Okay, and C5 is greater than C5s. Okay, so in isentropic case we got an velocity of 663.2 and here we are getting 637. Okay, so we can see the actual velocity is lower than that we get in the non-isentropic case. Sorry, in the non-isentropic case, the or the actual flow velocity is lower than the exit velocity that we will get if the nozzle was operating in isentropic condition. Okay, so this is also what we saw in the initial in our from the TS diagram. Okay, right? Is this clear? Any questions in this? So this sort of explain how we draw a TS diagram for the nozzle and how we can compute the exit velocity. Okay, given the nozzle isentropic efficiency. Okay. Any questions? else we can move to the next part where we can discuss about nozzle choking and how uh, this sort of computing the nozzle exit condition changes if the nozzle is choked. Okay, let's move on. Okay, so let's say this is let's say we are considering a simple turbojet engine at sea level static conditions where ambient pressure and temperature, ambient pressure is 1 bar and ambient temperature is 288 Kelvin. Okay, so we have a nozzle. Okay, so ambient condition PA is 1 bar and temperature is 288 Kelvin. Okay, so at the nozzle inlet we see that so it's saying that turbine exit total pressure. So turbine exit be nozzle inlet, so there the total pressure is 1.878 bar and the total temperature T04 is 877.8 Kelvin. Okay, and the nozzle isentropic efficiency is 0.95. Okay, so this is your gamma and this is your Cp. All right, so first question is find the critical temperature and critical pressure ratio of the nozzle. So what is that? So as we have seen that, so nozzle, so this in case of, so this is a turbojet engine, right? So the flow at the entry of this nozzle will be subsonic. Okay, the Mach number less than 1, right? Mach number less than 1. Okay, and as the gas goes through the nozzle, the flow velocity increases and the Mach number of the flow also increases, right? So when we say the flow is choked when the Mach number at the exit of the nozzle becomes equal to Mach number 1, right? So that's when we say that the nozzle is choked. Okay, so for a, as we have seen that for a nozzle given the upstream conditions, there is a particular, or you can say there is a particular pressure ratio at for which for a given nozzle there is a particular pressure ratio which is the stagnation pressure at the inlet divided by the static pressure at the outlet. So that nozzle pressure ratio, if the nozzle pressure pressure ratio is at a particular pressure ratio, that nozzle gets choked, and if you increase the pressure ratio beyond that, the flow rate won't change. So that is what we have seen is a nozzle choking condition. Okay, so so we see that for when we will do this sort of analysis for a aircraft engine. Okay, so we'll know the total pressure of the nozzle. So total pressure at the nozzle inlet and what is the pressure at the nozzle, what is the ambient pressure at the nozzle exit. Okay, so from that we can get a pressure ratio. Okay, P04 by PA. Okay, so this is 1.878 divided by PA is 1 bar, so this is 1.878. Okay, all right, so this is our the pressure ratio between the inlet of the nozzle and the ambient conditions. Okay, so this is the maximum this is the maximum pressure ratio possible for the nozzle. Okay, so now we have to see what is the critical pressure ratio. Okay, so first let's us do what is the critical temperature ratio. So that is our T04 by TC being the critical temperature. So TC is the critical temperature, which means that the temperature attained if the flow at the exit of the nozzle is sonic or the Mach number is 1. Okay, so then that is given by gamma plus 1 by 2. So this condition we derived in the last session, you can go back and see. So total temperature by the temperature is equal to gamma plus 1 by 2 if the flow is sonic at the outlet of the nozzle, and that is equal, that temperature we say is the critical temperature. Okay, so we have to find out the critical temperature ratio. So that is 1.333 plus 1 by 2, so that is 2.333 divided by 2 is equal to, so T04 by Tc, this is the critical temperature ratio, this is 11665. okay, so this is our critical temperature ratio. Now we have to compute the critical pressure ratio. All right, so for a when the nozzle isentropic efficiency is given, the expression for critical pressure ratio, this is also has been derived in the last week's lectures. Okay, that is given by 1 by 1 plus minus, this is an eta nozzle isentropic efficiency. Now within brackets you have gamma minus 1 by gamma plus 1, the entire denominator raised to the power gamma by gamma minus 1. okay, so this is what we get when this is the this is the expression for critical pressure ratio for a nozzle when for a given value of nozzle isentropic efficiency eta nozzle. Okay, sorry, what are you saying? I didn't get you. Minus, yeah, so numerator will be gamma by gamma minus 1. okay, so the denominator raised to the power this. okay, so like if you see that, if you put if you put minus, then it will be the entire thing. Let me check it again if you are pointing it out, just second. No, this is all right. Okay, so I'm just raising the not just, it will be minus gamma by gamma minus 1 if you say you are raising the entire thing. I'm just raising the denominator to this power. Okay, so this is correct. All right, so now if you see, if you now put just to show you, if eta nozzle is equal to 1, you will see that P04 by Pc. So if you just put eta nozzle value equal to 1 here and simplify this expression, what you will get is P4 by Pc will be equal to gamma plus 1 by 2 whole to the power gamma minus 1 by gamma. Okay, so which is equal to T04 by Tc gamma minus 1 by gamma. Okay, so this is basically your isentropic relation, right? Isentropic relation, because if eta nozzle, the isentropic efficiency of the nozzle is 1, this simply which in there, that signifies that our nozzle is operating in isentropic condition, or the flow is isentropic, which means that the isentropic relation will be valid between the critical pressure ratio and the critical temperature ratio, right? Okay, all right, so let's proceed with this. Okay, so now we have to also find out the critical pressure ratio. Okay, so this was the explanation part. So the critical pressure ratio P04 by Pc will be, so if you just, you have to here put in the values, 1 divided by 1 minus 1 by 0.92, sorry 0.95, this is gamma minus 1 is 0.333. remember, here we are dealing with exhaust gases, and so the gamma value is 1.333, and this is denominator is gamma plus 1, 2.333. okay, and this will be raised to the power gamma by gamma minus 1, gamma is 1.4, sorry 1.333, and gamma minus 1 is 0.333. okay, so if you solve this, you will get the critical pressure ratio as 1.914. okay, so next thing is goes to a question. So if we have to find out the critical temperature and pressure ratio across the nozzle, and then we have to determine whether the nozzle is choked or not. Okay, so so you have to see that, so nozzle is choked if P04 by PA is greater than P04 by PC. Okay, so if the existing pressure ratio so the pressure ratio between the nozzle inlet and the nozzle and the ambient condition, that ratio is greater than the critical pressure ratio, then the nozzle is choked. Okay, so what that this means that so as you are going across the length of the nozzle, the pressure is decreasing. Okay, so but there will be but if it reaches PC, okay, then the the nozzle pressure ratio cannot decrease further. Okay, so at the nozzle exit, this will be greater than, yeah, right, P critical, yeah, or you can say that PC has to be greater than PA, right? You can also do it like that, but generally we check the in terms of the nozzle pressure ratios. Okay, so nozzle, so what we here we have seen uh, for the given problem, P04 by PA, so that value is 1.878 is less than P04 by PC, so this is what we get, 1.914. Okay, so which indicates that nozzle is not choked. Okay, so if the nozzle is not choked, nozzle exit pressure is equal to ambient pressure. Okay, which means that P5 is equal to PA. All right, so when you should remember that if when the nozzle is not choked, the nozzle, so means that the gas can expand fully to the ambient pressure within the nozzle. Okay, and P5 will be equal to PA. All right, but if the case is different, let's say your nozzle is, yes, Mach number is greater less than 1, right? Mach number will be less than 1. We'll see that. So if it's just, you see, the next question is we have to find out the Mach number at nozzle exit. We'll see that it should come out less than 1. Okay, we'll compute that. All right. Okay, so this is the thing. So you see, so okay, but another thing, if nozzle is choked, then nozzle exit pressure will be equal to critical pressure. Okay, which means that P5 will be equal to, so if nozzle is choked, this is the, I'm saying the giving you the context when the nozzle will be choked. So if the nozzle will be choked, the nozzle exit pressure P5 will be equal to the critical pressure. Okay, and that is actually greater than the ambient pressure. Okay, so let's say, so what we will see that, so in the nozzle this will be equal to PC, and in the ambient the pressure is PA. So if the situation will be like this, so just at the nozzle exit you have a higher pressure compared to the ambient. Okay, alright, so this is kind of like what we say so this is like an under expanded condition. If you remember, the nozzle exit pressure is greater than the ambient pressure. Okay, so this is sort of so when you have nozzle choking, you have sort of an under expanded condition. Okay, alright, okay, so this is not, this we'll see problems with nozzle choking in one of the later problems today, but yeah, but for this problem the nozzle is not choked. Okay, alright, so let's find out what we have to find out next. We have to find out the Mach number at nozzle exit. Okay, alright, so Mach number at nozzle exit, so this is like M5, so this should be equal to the C5 by A5. So A5 is the speed of sound at nozzle exit conditions, right? Okay, so first we have to find out C5. Okay, so So remember what is C5? We derived it in the last problem. So C5 is 2 Cp times T04 minus T5, right? Right, so this is what we have seen. So this is our nozzle exit velocity. So here we have to use a Cp for gas, T04 minus T5. Okay, so and we have to find we can find C5 from our um, the definition of nozzle isentropic efficiency, right? So our nozzle let's go back again. So if our nozzle isentropic efficiency is T04 minus T5 divided by T04 minus T5s, right? So this is 1 minus T5 minus T04, 1 minus T5s minus T04. So this we can write in terms of the pressure ratio, right? P05. What do I made a mistake? A second. This is like, sorry, P5 by P04 to the power gamma minus 1 by gamma. Okay, so if you simplify this, you will get this expression T04 minus T5. This is like similar to what we get in case of turbine and isentropic efficiency. Alright, so this is 0.95 times T04 was given as 877.8, 1 minus, so P04 by P5, which so which is P04 by P5. Okay, so our, since this is unchoked, right? So nozzle exit pressure is equal to the ambient pressure, so 1.878. so P05 by P04 by P5, that should be equal to P04 by PA is equal to 1.878, right? This will be our nozzle exit the pressure ratio across the nozzle. So 1.878 whole to the power 0.333 divided by 1.333. okay, gamma is 1.333. so this will give the temperature difference as 121.6 Kelvin, and T5 will come out as 877.8. so this is the temperature difference, and this will come out as 877.8 minus 121.6. so T5 will come out as 756.2 Kelvin. Okay, all right. Is this clear till this point? Okay, so now this part is now similar to the last problem. So we are finding the actual the part B and C of the last problem. So we are finding the actual exit temperature at the nozzle, the static temperature at the exit of the nozzle from using the nozzle isentropic efficiency and the pressure ratio, right? So after that we can compute the velocity, right? Okay, So next we have to compute the velocity. Velocity is c5. So c5 is equal to 2 cp times T04 minus T5. So this is 2 times cp value is what is the cp value? 11. Just let me check. Yeah, cp value is 1147. This is 1147 and the temperature difference is 121.6. okay, so c5 we will get as 528.3 meter per second. Okay, so we know the value of c5. Okay, next we have to compute the Mach number. Okay, so for Mach number is equal to c5 by a5. Okay, first we have to compute a5. Okay, so okay, can anyone tell me what is a5? So just let me tell you. So gamma value is, so you need gamma, R and temperature, right? Okay, so gamma value is 1.333. Okay, R you can take, so R is not given, so R you can compute that Cp is equal to gamma R by gamma minus 1. Cp is 1147, gamma is 1.333 into R by 0.333. So R should come out 1147 into 0.333 divided by 1.333. Okay, so R is coming around 286.53, which is like 287 only, like what we generally use. 287 joule per kg Kelvin. Okay, so we know R and gamma and temperature. Can anyone compute and tell me what is the value of the speed of sound and the Mach number? Just compute. So you know everything. So what is the value of the speed of sound? Square root of gamma times R times temperature, right? Yeah, just compute and tell me. And what is the value you are getting? It shouldn't take this long. What is the temperature value? Which temperature value you should take here? Yeah, not T05, T5. Okay, this is Mach number is, we have to take the static temperature. Okay, so gamma R T5. Okay, so this is 1.333, R is 287 and temperature is 756.2. okay, so to take the Mach number is always based on static temperature, like the speed of sound is based on static temperature. Okay, so this will get as, anyone got the value? Just tell me. So Mach number will be C5 by A5. C5 is, what is C5? Yeah, 537 point, let me just check these ones. 1.333 into 287 into 756.2. Yeah, 5, I'm getting 537.86. Yeah, okay, so 537. Okay, so C5 was 528.3 divided by 537.86, right? So this is less than 1, right? So 528.3, yeah, so Mach number is 0.98. all right, okay, so this is clear. So we have seen that the nozzle is not choked, okay, and that's we are also getting the Mach number at exit less than 1. Mach number at exit is less than 1, okay, because the nozzle is not choked, okay. And also see, look, one interesting thing to note is that you can see here that the actual pressure ratio is very close to the critical pressure ratio, right? So that's why the Mach number is exit Mach number is very close to 1, okay. You can see this is almost, it is 1.88 and this is 1.9. So it's the pressure ratio, nozzle pressure is very close to the critical pressure ratio, right? So that's why the exit Mach number is also close to 1, very close to 1, okay. Is this clear? So this was sort of a thing how you solve problems related to nozzles, okay. This, like, nozzles will come up in, like, when you will do like full thermodynamic analysis of the aircraft engine cycle. We have seen by part how to do a thing considering just intake, nozzle, compressors and turbines. We have done many times by the computations using isentropic efficiency. All right, so this is how you do it for nozzle. Any questions? Then if not, we can move on. Okay, I hope this is clear. Okay, so any other parts I missed? Yeah, so in this problem we have seen to find out the critical pressure ratio of the nozzle and how we determine whether the nozzle is choked or not. And we have, for this case, we have seen that the nozzle is not choked, and we have seen that the Mach number is also, that's why comes less than 1, okay. This is the part B of the problem done, okay. Okay, so now we have a few MCQs, so I will like you to answer this in the chat box, okay. So first we have is a match the following. So on the left we have 4 isentropic efficiencies and we have to match them with the definitions, okay. So you have nozzle efficiency, intake ram efficiency, compressor efficiency and transmission efficiency. So which is the correct option? Yeah, right, correct option is option C, okay. So nozzle efficiency is 4, we just described this is actual kinetic energy rise by ideal kinetic energy rise, okay. So option intake ram efficiency is Roman 3, which is real pressure rise by isentropic pressure rise, okay. So for intakes we have seen that we can define it as an isentropic efficiency. Isentropic efficiency is defined in terms of temperature differences, or it starts with an like we generally express it in terms of enthalpy differences, and which we can simplify to a ratio of temperature differences, assuming constant Cp, okay. So for we have seen the problems we did, in that case we considered the intake isentropic efficiency, but in the similar way we can also define intake ram efficiency, and that is defined in terms of pressure differences, okay. Compressor efficiency we did that is 3, that matches to Roman 2, that is ideal compressor work by actual compressor work. Isentropic or ideal compressor work is lesser than the actual compressor work, so that's why it is defined in that way: ideal compressor work in the numerator and actual compressor work in the denominator. And last we have transmission efficiency, and this we have used in the in our problems in last problem solving session, which is like the is associated with the the compressor work divided by the turbine work required to drive the compressor. Okay, so there is this, we have seen that transmission efficiency is a mechanical efficiency accounting for the losses due to friction in the during the transmission shaft, and that is generally around 98 to 99%. Okay. Okay, so moving on to the next one. This is also an easy one. We have to choose the correct path of air from inlet to the outlet of the hot nozzle of a turbofan engine. Which is the correct option here? Rating. Right, this is also C. So let me just draw a schematic. So this is my axis. Okay, so first we have the fan here. Okay, so after the fan, the flow gets split into two parts. So this is my cold nozzle, right? And then in the around the center line we have the hot nozzle. So it's like the flow is divided into two streams after we have the fan here. So this is our fan. So then we have the compressor. Okay, we have the compressor. So this is compressor. Okay, then we have combustion chamber, right? Then we have the high pressure turbine. Let's say we have, this is a, what I am doing is a twin spool turbofan. We have like two spools, okay, two shafts. So one is our red two shafts basically. One is the red one, okay, and one is the orange one. Okay, so then after that we have a low pressure turbine. Okay, and then after that we have the hot nozzle. Okay, so this is, so we have been asked to the question for the inlet from the outlet of the hot nozzle. So we have fan, compressor, combustion chamber, high pressure turbine, low pressure turbine, then nozzle. Okay, so the correct answer is option C. Okay, and the cold stream we have just fan and the cold nozzle. Okay, all right. So question 5, in twin spool turbofan engine, this is just related to the previous question, fan is driven by low pressure turbine, high pressure turbine, high pressure compressor. Option D, other external sources. This is the correct answer. Yeah, 5A. Okay, so just we will go back to the diagram. So you see that the compressor is driven by the high pressure turbine, and the fan that is driven by the low pressure turbine. Okay, all right. Question 6, this now we have a few questions on ramjets now. So ramjets engines are highly suited for, options are subsonic application, supersonic application, hypersonic application. Option D, none of the above. Yeah, right, supersonic. Okay, so supersonic is Mach number greater than 1, in between Mach number of 1 and 2. Okay, if you want a speed higher than like Mach number over Mach, generally 2.5 or 4, then we have to go for scramjets, which is like hypersonic speeds. Okay, Okay, next question again on ramjets. For ramjets, the incoming air is compressed using, the options are axial compressor, centrifugal compressor, reciprocating compressor, option D oblique shocks and diffuser. Which is the correct answer here? Sorry. For ramjet engines, the incoming air is compressed using anyone? Okay, no guesses. Okay, so in ramjets, let me draw a schematic of the ramjet. So we have something like this. Okay, okay, so ramjets, just remember ramjets and scramjets do not have any turbo machinery. What is turbo machinery? Turbo machinery is our compressors and turbines. Okay, so like turbines. Okay, so how then the compression takes place? Okay, so in case of ramjets, you get shocks like this. These are like oblique shocks. Okay, then you have diffuser. Okay, so here the flow is approaching with Mach number greater than 1. Okay, so after you encounter a shock and then you have a diffuser, so here then you have the combustion chamber, and then finally you have the nozzle. Okay, right, so you see you have diffuser, so here the flow Mach number becomes less than 1. Okay, so after you encounter the shock system and diffuser. Okay, so in the combustion chamber we have Mach number less than 1. After that you come up with this nozzle. So you see I have sort of drawn a CD nozzle, right? CD nozzle. So this, remember we had a question in the last session that what types of nozzles are used in your ramjet. So this is CD nozzle, because the flow needs to be accelerated to, the exit flow needs to be accelerated to supersonic speeds as well. Okay, because to generate forward thrust, because the aircraft speed CA is Mach number greater than 1, so the nozzle exit velocity also has to be supersonic, the Mach number greater than 1, right? So that's why we use a CD nozzle. All right. Okay, so this is, so in this case the inlet air is compressed using oblique shocks and diffusers. Okay, so remember again the operating principle of diffuser. In diffuser the velocity decreases and the pressure increases. Okay, so that is also, the compressor is also equivalent to increase in pressure, right? So diffuser also increases pressure. All right, so and if you have studied gas dynamics, you have seen that when you have an oblique, when you have a shock, the pressure increases across the shock, the static pressure increases across the shock. Okay, so that's how compression is achieved in case of ramjets. Okay, and we don't have any rotating parts. Okay, so remember in case of turbojets and turbofan, the turbine, the fans or compressor are the turbo machinery, and that all that is absent in the ramjets. In ramjet, we since we don't need a compressor, the and that's why the turbine is needed to run the compressor, drive the compressor, that is also not needed. So that's why it's simply just we can get rid of all the turbo machinery, okay, and all the compression happens by the big. So in this case of ramjet, the design of the intake, design of this intake diffuser and this strut, this protruding strut at the that is very important, so that you get the shock system correctly and the diffusion process correctly to get the desired pressure rise. Okay, all right. Any questions? Okay, let's move on. Okay, this you should be able to answer. In case of a ramjet engine, air enters the intake at dash speed and encounters combustion at dash speed in the combustion chamber. Okay, so options are supersonic. In think carefully. I just explained it in this. So this is supersonic. Okay, but when it goes to the combustion chamber, it is subsonic. No, D is obviously not the at intake the speed is supersonic, that is for sure, because ramjet engines are used for supersonic flights. Okay, so at intake this flow Mach number is greater than 1. So after that it gets this shock systems. We have this, then we also have a normal shock here, it depends on the intake design. Okay, so then we have the diffuser. So ultimately when it reaches the combustion chamber, the flow Mach number is less than 1. Okay, so the option is, correct answer is option C. Okay, so it enters the intake at supersonic speed and combustion happens at subsonic speed. Okay, for ramjet engine. When you have scramjets, which is like okay, then in scramjet you have generally supersonic, like, or generally hypersonic speed at intake, and the combustion is also supersonic. All right, so that is the main difference between the scramjet and ramjet. Okay, so like so if you see this the spelling, right, so this is like ramjet is generally called like, this is like supersonic combustion ramjet. So that's why this S and C comes, you can say scramjet and ramjet. Okay, SC. All right, so that is like the difference between scramjet and ramjet engines. Okay, that's why scramjets also generally go to hypersonic speed, so that is pretty largely supersonic. Okay, okay, this is clear so far? Any questions? Okay, thank you. Okay, let's move on. So question 9, in an ideal ramjet with an unchoked nozzle and fuel air ratio is less than 1, so details of the oblique shock, you have to take a gas dynamic course. So you know about normal shock. So in normal shock, okay, just you know about normal shock, Sehbaz? So in normal yeah, so in normal shock, this is like for 1D flow. So we have a flow approaching, so this is Mach number greater than 1. and have this is Mach number less than 1. So this is a very infinitesimally small structure across which there is a sharp change in pressure, temperature and velocity. Okay, so the flow velocity decreases, pressure increases, temperature increases. Okay, so this is normal shock. And when you have oblique shock, this is for 1D flow, but in general the like this is like flow is generally essentially one dimensional. So when you have oblique shock, so this is like, let's have a two-dimensional flow. So let's say here something like this. Slow the flow has to, let's say we have something like this, the flow turning. So you'll get a shock like this. So flow is in that direction here, and after the oblique shock the flow turns around this like this. Okay, so this is like generally encountered in, so when the shock wave is not normal to the flow direction, that is what is we can say oblique shock in layman's term. Okay, but if you want to go more in details out there, you have to take a gas dynamic course. Okay, so this is how an oblique shock looks like. Okay, basically you can say this is like for a, what I draw, this is like essentially a 2D flow, two-dimensional flow, right? Have two components where both x component and y component of velocity. So it is in the x direction, and then when the flow turns there is also a y component of velocity, and the shock sits in somewhere in between. Okay, all right. Okay, so next question, for an ideal ramjet, the conditions are the nozzle is unchoked and the fuel air ratio is much less than 1. The thrust can be expressed as, so we have given this pi b is the temperature ratio T04 by T02. Okay, so let me just go back and just say what is T02 and T04. So remember what professor discussed in the lectures. So this is A, station A, ambient. So this is what we call state point 02, to be consistent with the thing that we don't have a compressor, but compressor exit and combustion chamber inlet, that we used to denote by state point 2 in our turbojet, or like in any Brayton cycle analysis, right? And the nozzle inlet we used to denote as state point 4. Okay, right? So that's why we keep the same things here. Okay, and then so that's how, and so here the, and that's how we keep the state points. Okay, that's how we define the state points in the nozzle. Okay, and this is again M5. Okay, so this is how it is, the state points are defined in case of a ramjet, and the TS diagram looks like this. Okay, so we have A2 02, then 02 to 04, and then 04 to 5 is our nozzle. Okay, so A202 is our intake plus compression process, 02 to 05 is our heat addition or combustion chamber, and 04 to 05 is our expansion through the nozzle. Okay, so this is these 2 and 4 are just chosen to be consistent with the station numbers in case of a simple turbojet engine. Okay, all right. So this is T04 by T02 is our that temperature ratio. Okay, so next thing is we have to consider what is the expression for thrust. Okay, in terms of this. Okay, so in the lecture, professor has discussed an expression for thrust in terms of considering the fuel air ratio, but here we have seen that it said that the fuel air ratio is very very less than 1, so we can neglect that. Okay, so let's see. Okay, first so let me draw the TS diagram again here. So A202, this is 04, this is 5. Okay, so P0A by PA, that is equal to 1 plus gamma minus 1 by 2 ma square by 2 gamma by gamma minus 1, right? And P05 by P5 is equal to 1 plus gamma minus 1 by 2 m5 square by gamma minus 1. Okay, so this is like we are considering an ideal ramjet. So since it is ideal, so gamma at the inlet and outlet is same. Okay, that's an assumption here. Okay, okay, because we are doing ideal ramjet. Okay, so now if we look at here, now PA has to be equal to P5. Okay, so since this is an unchoked, okay, since the nozzle is unchoked, which means that the nozzle exit pressure will be equal to the ambient pressure, right? So PA is equal to P5. Okay, which means that P0 is equal to P05. Okay, all right. Okay, and this will imply that Mach number is the same. Okay, okay, so you can see this. So if you now here I express this in the terms of the pressure ratio, but just give me a minute, let me check one thing. Sorry about that. Yeah, right. Okay, so if you now look at this, so you will get the Mach number at inlet is equal to the Mach number at exit. Okay, all right. So this sorry, okay, so the MA is equal to ME M5. Okay, so Mach number at inlet is equal to Mach number at exit. This is the condition for ideal. This is valid for ideal ramjet with constant R and gamma. Okay, they were assuming that a gamma and R is constant, so that's why we can write this. Okay, so this means that what is this is UA by or yeah, so this is inlet velocity or the UA by AA, right? So the aircraft speed by the speed of by the local speed of sound divided by the exit velocity U5 divided by the this thing. Okay, so this you will get U5 is equal to UA times A5 by AA, right? So UA is equal to square root of gamma R T5 equal to gamma R TA. Okay, so what we get is U5 is equal to UA times square root of T5 by TA, right? Is clear till this point? Okay, so now so this is T5 by TA. Okay, but we wanted we wanted something in terms of the total temperature ratio. Okay, so what we do here is okay, now T05 by T5 is equal to 1 plus gamma minus 1 by 2 M5 square, right? And T0A by T5, that is equal to 1 plus gamma minus 1 by 2 MA square, right? So this is, I'm just writing the stagnation temperature ratio, the relation between stagnation and static temperature at the ambient, at the inlet of the ramjet and at the exit of the ramjet, okay, at the exit of the nozzle, okay. So, and we have seen, so this is the relation, and we have seen that M5 is equal to MA, okay. Okay, now since M5 is equal to MA, so you can see on the, so the right hand side of both these expressions become equal. So this will indicate that T05 by T5 is equal to T0A by TA, which is T5 by TA is equal to T05 by T0A, okay. Alright, so we can write U5 is equal to UA times T5 minus TA, right? So this we can write UA times T05 minus T0A, okay. Alright, now T0A is equal to T02 and T05 is equal to T04. Why is that? So let me go back to this thing, okay. So between A and 2 right, there is no heat addition or work transfer, right? Agreed? So T0A is equal to T02 right. Similarly, we have a nozzle inlet is 4, nozzle exit is 5. So, and in the nozzle we know nozzle is adiabatic, no heat transfer, no work transfer. So T04 is equal to T05, okay. And between 2 and 4 in the combustion chamber we have heat addition, right? So obviously the stagnation temperature increases there. So here T04 has to be greater than T02, okay. So is this clear now? So the stagnation temperature we have in the ambient, and the stagnation temperature at the end of a diffuser remains the same because there is no heat loss, okay. Similarly in the nozzle there is no heat loss or no work transfer happening, so the stagnation temperature stays constant. Alright, so that's why that's how we come up with this, okay. So okay, for the ramjet this is true, okay. So therefore we can write U5 is equal to UA times T05 by T0A. So this we can write T04 by T02, okay. And this T04 by 202 is represented by tau B here, okay. So U5 becomes UA times tau B, okay. Is this clear? So okay, let me repeat what I said. So for an ideal ramjet we should remember, if the nozzle is unchoked then we can write the pressure ratio, and from that we can since PA is equal to P5, and we come up with the condition that the Mach number at inlet and exit has to be equal, okay. So since the Mach number at inlet and exit are equal, so we write this in terms of the velocity ratio, local velocity divided by local sonic speed, okay. And we simplify this in terms of year, so we get U5 is equal to exit velocity equal to inlet velocity times square root of exit temperature by inlet temperature, okay. And since the inlet and exit Mach numbers are same, the ratio of static temperature at the exit and the inlet is equal to the ratio of static temperature at the exit and inlet, okay. So which we put in here, and now we have seen that the stagnation temperature at inlet is equal to the stagnation temperature at the exit of the combustion chamber, and stagnation temperature at exit is equal to the stagnation temperature at the inlet of the nozzle or at the exit of the combustion chamber. Okay, so there we can simplify and come up with this. Okay, so now finally the expression for thrust. So thrust is T is equal to m dot times 1 plus F into U5 minus m dot F times UA, right? So the momentum flux going outward, so there the total mass flow rate is the mass flow rate of air plus fuel times the exit velocity minus this. So if we now neglect, since F is much less than 1, so thrust will be equal to, okay, let me do it in a new page. Okay, so thrust is equal to m dot A times UE minus m dot A times UA. Okay, so this is m dot A UE minus UA. So UE is UE times UA times square root of pi b. Okay, so I am using this expression there. The exit velocity is equal to the inlet velocity times square root of this temperature ratio, stagnation temperature ratio across the combustion chamber. All right, so we are invoking that. Okay, so now if we take UA common, this will be equals to m dot A UA times square root of pi b minus 1. Okay, so this is our answer. Okay, so which is option C. Okay, is this clear? So in the if you look at the this derivation is also done by the professor in the lectures, but he went on with this. So he derives till this expression that U5 is equal to UA times square root of the stagnation pressure ratio, and then he derives the expression without neglecting the fuel air ratio. Okay, so like if F is not negligible, we will come out with an expression something like this: T by m dot is equal to ma times square root of gamma RTA. So this is basically UA 1 plus F square root of T04 by T02 to 1 plus, so you get some the complicated expression like this. Okay, so this is what is derived in lectures. Okay, you can look at it. Okay, but if you simplify, don't like F, if you don't consider F, so you can reduce it to something like this. Okay, all right. Any questions? Okay, let's move on then. Okay, so question 10: for a given Mach number, the specific fuel consumption of a ramjet engine increases with maximum engine temperature, decreases with maximum engine temperature, initially increases then decreases with maximum engine temperature, doesn't change with maximum engine temperature. What will be the answer here? So what is SFC? SFC is specific fuel consumption, right? And what is our maximum engine temperature? This T04, right? Temperature at exit of combustion chamber or inlet of nozzle, right? So that is where we'll get the maximum engine temperature, right? Okay. In when we have turbojets and turbofans, the maximum temperature is at the entry of the exit of the combustion chamber, but at the entry of the turbine. Okay, but since here we don't have a turbine, it is the maximum engine temperature also happens at the inlet of the nozzle. Okay, so like this is like, if you think logically, so if you want higher engine temperature, right, higher engine temperature means that you have to burn more fuel for a given thrust, right? And thus if you want higher temperature means that you have to burn more fuel generally. Okay, so SFC will
See, sir, first increases and then decreases.
yeah second let me yeah so SFC increases with increase in temperature, it will increase. Okay, no, it's not non-monotonic, it's monotonic. Okay, so this is think logically. So if you want to achieve more engine temperature, we have to increase the fuel consumption, right? Burn more fuel. If you burn more fuel, you will get higher temperature. Okay, so like there is this plot we can see. So this is SFC versus Mach number. Okay, so this plot goes like this. Okay, okay, so now if you go on increasing T04, it follows this trend. Okay, okay, so with Mach number it sort of decreases and stabilizes, but if you keep on increasing the maximum engine temperature, which is T04, okay, so it sort of follows this trend. Okay, so SFC increases with increasing engine temperature. Okay, so this plot was also like the expression for SFC was derived when this plot was drawn in also in the lectures. Go back and check that again to clear if you have any doubts. Okay, okay, so the next question 11, consider the following statement regarding the specific thrust of ramjet engine. Okay, so you have specific thrust, so specific thrust is T by m dot. Okay, so this is specific thrust. Okay, the options are: it decreases continuously with Mach number for a given maximum temperature of the cycle. It initially increases then decreases with Mach number for a given maximum cycle temperature. It decreases of statement 3, it decreases with increasing maximum total temperature for a given Mach number. Or option statement 4, it increases with increasing maximum temperature for a given Mach number. Okay, so just second, so we'll just draw this variation. So you have T by ma with Mach number. So this is, I am plotting this expression basically, this one. This expression. Okay, so you see here T by m dot is the specific thrust, so it depends on Mach number. So you have Mach number here and also Mach number here. So you see there a Mach number appears in two places here, so that's why your yeah, so Mach number appears in two places here, so that's why you have to be so this is like non-monotonic. Okay, so the plot looks like this. So the specific thrust initially increases and then decreases with Mach number for a given cycle temperature. Okay, so this is for a given cycle temperature, so this is like for a constant value of T04. Okay, so you can see here this is the specific thrust sort of as a direct relationship with T04. So if T04 or maximum cycle temperature increases, the thrust should also increase. Okay, so now if you keep on increasing this thing, so it will follow this trend. Okay, so each curve is at a constant value of T04. Okay, and if you increase T04, the curve shifts upwards. Okay, so if you refer to this curve, So statement 2 is right. It initially increases and then decreases with Mach number for a given maximum cycle temperature. Okay, and statement 4 is correct. It increases with increasing maximum total temperature for a given Mach number. So if you, let's say, fix a Mach number at a point, okay, so this is like a vertical line. So if you now go from this Mach number, so if you now go from this temperature, if you increase the temperature, so your specific thrust will increase. So statement 4 is right. So correct answer is option D. Okay, so if you remember these two plots, like for ramjets, important, what is that is the variation of SFC with Mach number and maximum cycle temperature. Okay, so for SFC we have seen the plots looks like this. It sort of decreases with Mach number and saturates at the value, but if you increase the maximum cycle temperature, SFC will increase. So and for the specific thrust, so it will increase with Mach number and then start decreasing for a given value of T0, for a given value of maximum cycle temperature T04, and if you increase T04, the curve shifts upwards. Okay, all right, so these are the variations. Okay, any further questions? Okay, okay, if you don't have any questions, we can quickly move on to the last problem, numerical. So this is sort of similar to the last assignment question. You have a set of questions on turbojet engines, so I will just try to solve this. So I will sort of do this quickly because we are short of time, and but the individual parts, like this kind of problems we have done before, but now we are doing it first time for a turbojet engine, so the things will be slightly different, but we have individually done analysis of each of these components, like intake, compressor, turbine, then nozzle also we did today, and then the work matching between intake and turbines and all these things we have done. Okay, so let's start. So I have the nozzle turbojet engine with a flying with a Mach number of 0.8. Okay, and what has given is the compressor pressure ratio. So this is RPC, turbine inlet temperature. Okay, first let us draw a TS diagram. This will be easy then. Okay, so this is state point 01. Okay, from here we go to this, sorry, go to state point 02. So 1 to 2 is a compressor. Okay, right, so 0 to prime is our isentropic state. So we have 1 to 2, so this is our compressor. Okay, so then we have the combustion chamber. So generally there is a pressure loss in the combustion chamber, so this is delta PCC. So this is our state point 03. So from here we have expansion through the turbine first, so this is 04, and after that we have the nozzle. Okay, so 4 to 5 is our nozzle. Okay, so all like for each we also have their corresponding isentropic state, which is represented by prime. Okay, so this is sort of the approximate TS diagram showing the state. Okay, so 1 to 2 is the compressor, 01 to 02 is the compressor, then 02 to 03 is the combustion chamber, but here we are accounting for a pressure loss delta PCC. Okay, because it's a real cycle. Then we have turbine here, and then we have 04 to 05 is the nozzle, like the standard state point numbering which we have also used in our earlier problems. Okay, so so our compressor pressure ratio is RPC is 9, turbine inlet temperature is 1350 Kelvin, so that is T03. Isentropic efficiency of compressor is 0.9, so eta C. Isentropic efficiency of the turbine, that is eta T. Isentropic efficiency of the intake, that is eta intake. Isentropic efficiency of the nozzle, that is eta nozzle. Okay, then we have mechanical efficiency, eta mech. Then we have the combustion chamber pressure loss, so that is delta PCC. Okay, so that is generally, we have seen that is generally expressed as some percentage of the compressor combustion delivery pressure, which is like P02. So this is 0.05 of P02. Okay, the fuel air ratio is given 0.194, 0194. The gas constant is 287 R. So this shouldn't be universal gas constant. This is a mistake. This should be just a gas constant, specific gas constant. Okay. Then we have the ambient pressure. So ambient pressure PA. This is PA. This is TA. Okay, and the speed of sound. Okay, and we have been given the specific heat at constant pressure, and for air. So this is, sorry, so we have been given the gamma value, gamma and CV values for air, and gamma and CV values for the exhaust gas. Okay, so let's start the problem. So this is generally the things we have been given. First is we have to let's see what is being asked for. First question is total pressure at the outlet of the compressor. Okay, so outlet of the compressor is state point 02. So basically we have to find out P02. Okay, so we have to start with P01. Okay, so just remember, so we have to start with the intake. So this is the relation, P01 by PA is equal to 1 plus eta intake times CA square by 2 CPA times TA all to the power gamma A by gamma A minus 1. Okay, so this is the, if you remember the last class we did, this is the expression for pressure ratio across the intake. The stagnation pressure ratio at the exit of the intake divided by the ambient pressure is given by this expression. Okay, so I have to find out CA here, CA first. So CA is equal to Mach number times gamma R TA. Okay, or Mach number times the speed of sound. Okay, so Mach number is given 0.8 and the speed of sound A is given 299.5. so CA we get as 239.6 meter per second. Okay, so now once we know CA, we can put it into the values here. Okay, so P01 by PA will be equal to 1 plus eta intake is 0.95, CA square is 239.6 whole square divided by 2 CPA. CP is 1005, this is the air, CP for air, and the ambient temperature TA is 223.2 Kelvin. Okay, whole to the power 1.4 by 1.4 minus 1. So if you solve this, we'll get P01 as 30.3959 bar. So this is our pressure at the inlet of the compressor. Okay, so pressure, total pressure at compressor outlet, that is P02, that should be equal to the compressor pressure ratio times the inlet pressure. So compressor pressure ratio is 9 9 times 0.3959, so P02 will come as 3.56 bar. Okay, so it is option B. Alright. Okay, so this was only the first. So first we compute the total pressure at the inlet of the compressor using the nozzle isentropic efficiency, using the intake isentropic efficiency. Okay, and then if you multiply with the pressure ratio, we will get the outlet pressure. Okay, pressure at the compressor outlet. Okay, so next question, we have to find out the actual total temperature at the exit of the turbine. So turbine exit is state 04, set 4. So have to find out T04. Okay. So first for that we need to find out the what is the how much what should be the pressure ratio across the turbine. Okay, so this is our turbine, nozzle and compressor, right? So first we have to find out how much expansion is happening across the nozzle. For that we need to find out the turbine pressure ratio and temperature difference across the turbine. Okay, so for that we have to do work matching between compressor and turbine. Okay, so first let us find out what will be the compressor work. So for that we have to find out T02, which is the temperature at compressor exit. So this is T01 times plus T01 plus eta C P02 by P01 whole to the power gamma A minus 1 by gamma A minus 1. Okay, so this initially we are finding the total temperature at the exit of the compressor. Okay, using the pressure ratio of the compressor, inlet temperature and the turbine isentropic and the compressor isentropic efficiency. Okay, so this will come out as 469 4 sorry 496 point 496.09 Kelvin. Okay, we get T02. Okay, alright, so now we know T03, that is given as 1350 Kelvin, is the temperature at the inlet of the this thing. So the pressure at the entry of the turbine, that should be equal to P02 minus delta PCC, right? So there is a pressure loss in the combustion chamber. So if we subtract that pressure loss from the you can unmute and ask your question, Saibaz.
Sir, what is T01 value, sir? TA, sir.
Oh, sorry, I didn't compute it, right? Sorry, no, T01 will be just second. T01 is the total pressure temperature, right? So T01 is TA plus Ca square by 2 Cp. This is the total temperature, right? So T01 will be equal to T0A. The stagnation temperature in the intake will stay constant. Okay, so this is basically the stagnation temperature. So T01 will come out as 251.76 Kelvin. Sorry, I missed this part. Okay, this clear? Okay.
Yes,
So
yes, sir.
so remember, the stagnation temperature only changes when there is heat addition or work like some work transfer happening. So in the intake it is a diffuser, so there is no heat transfer or this thing. So what is the stagnation temperature at the inlet of the intake, what is in the ambient, that is the same as the which is, it stays the same at the exit of the intake or the inlet of the compressor. Okay, so that is our T01. Okay, all right, so P03 is the pressure at the entry of the combustion chamber minus the pressure loss. So this will give us the turbine inlet pressure. So this is P02 minus 0.05 P02. So P03 will come out as 3.38 bar. Okay. Okay. Next. Okay. So next we have to do work matching between compressor and turbine. So remember, the compressor work by turbine work is equal to our mechanical efficiency, right? So our compressor work is CPA times T02 minus T01. This is equal to eta mechanical times Cp of gas times the temperature difference across the turbine, that is T03 minus T04. Right? Okay. Alright, so this is 1005, this is T02. What is T02? 496.09 minus T01 is 251.76 to 0.99 times 1157 times T03 is 1350 minus T04. Okay. Alright, so if you solve this, T04 will come out as 1117 Kelvin. Okay, so this is our actual total temperature at the nozzle exit. Okay, so how we do is base doing the work matching between the compressor and the turbine. Okay. All right, so all right, so next question, we have to find out the critical nozzle pressure ratio. Okay, so you can I'm just skipping this part a bit. So if you know the turbine nozzle pressure ratio, so the turbine isentropic efficiency, that is the actual turbine work T03 minus T04 divided by the isentropic turbine work, right? C04 prime, right? So this is the this is the definition for your turbine work, right? Sorry, turbine isentropic efficiency. So from there, here you can obtain T04 prime. Okay, I don't have the values computed here, so you get the T04 prime from here. Okay, given because you know T03, T04 and T03 and eta T. Okay, so then we can get P04 by P03 as T04 prime by T03 whole to the power gamma gas by gamma gas minus 1. Okay, so you can use this to compute that pressure ratio, and from there you will get P04 as 1.586 bar. Okay, this is clear. So you first compute what will be the isentropic temperature, and then use the isentropic relation to obtain the pressure, the total pressure. Okay, so then we have to find out the critical pressure ratio, right? So nozzle critical pressure ratio, okay, so that is P04 by PC again. So this is, use this expression, 1 divided by 1 minus 1 by eta nozzle gamma g minus 1 by gamma g plus 1. This will deliver gamma g by gamma g minus 1. Okay. So if you do this is just a function of gamma and eta nozzle. This will come out as 1.92. Okay, so critical pressure ratio is 1.92. Okay, so and what is the our pressure ratio? This one we do P04 by PA, so that is 1.586 divided by our ambient pressure, that is 0.265. Well, this will come as 5.984. okay, so you can see here now in this case the total pressure at the nozzle inlet divided by the ambient pressure, that is very high, over close to 6. So this is the case for nozzle choking. Okay, so this implies that nozzle is choked. Okay, and what does this imply again? That our nozzle exit pressure will be equal to the critical pressure. Okay, all right, so that should be equal to your okay, so that should be equal to P04 by 1.92 will come out as 0.827 bar. All right. Okay, so the next part of the question, we have to find out the flow velocity at the nozzle exit. Okay, so here it is slightly different. We here the flow velocity won't be, we can't like directly apply the that relation. Okay, so here we know we can do what that. So at nozzle outlet, here we, if choked condition, we prefer to do it in a slightly different way. So the nozzle outlet, the pressure becomes equal to PC, which is 0.827 bar. So you see that that is higher than the ambient pressure because the nozzle is choked. Okay, and our T5, so here T5 will be equal to the critical temperature, and that is 2 by gamma g plus 1 times your T04. Okay, so remember the for the critical pressure, the critical temperature ratio is gamma plus 1 by 2. So we are using that here to compute the temperature at the exit. So that comes out as T5 will come out as 971.92 Kelvin. Okay, so this is our static temperature at the exit. So now what will be the flow velocity? So flow velocity is, remember that the flow is sonic at nozzle exit. which means Mach number is equal to 1. So our flow velocity is equal to the surface speed of sound, which is gamma g r T5, right? So here what we do, when the nozzle is choked, we can compute the temperature at the exit of the nozzle by using the critical pressure ratio, because when the nozzle is choked, the temperature and pressure will be equal. Temperature will be equal to critical temperature, and the pressure will be equal to the critical pressure, and we can obtain that critical temperature and pressure ratio. Critical temperature ratio is simple, gamma plus 1 by 2, and critical pressure ratio we can obtain from the is a function of gamma and the nozzle isentropic efficiency. Okay, so if we put these values, we'll get approximately 610 meter per second. That is our C5. All right, so now this is what we have got. So next thing is you have to compute the anyone has any question, can unmute and ask.
Sir, C question, what we have to calculate, sir? Nozzle critical pressure ratio.
Yeah, nozzle critical pressure. So this is this one, just
0.287, sir. 0.827.
no, not this one, this one. Critical pressure, nozzle pressure ratio is this one, P4 by PC. So this is just a function, you have to use this critical. So critical nozzle pressure ratio, you can, like, if you have just given the nozzle isentropic efficiency, you can just directly find the critical nozzle pressure ratio. You don't need the upstream condition or anything to determine whether the nozzle is choked or not. There you will need what is the inlet total pressure and the ambient pressure. Okay, so you have to find out here. So here what I so from the critical nozzle pressure ratio, we can identify that the nozzle is choked. Okay, and that's why our exit pressure, nozzle exit pressure will be equal to the critical pressure. Okay,
Okay, sir.
all right. Okay, so this is our so we once, so yeah, so the workflow goes like this. So first we find the compressor inlet and a compressor inlet condition using the intake efficiency, and then the compressor exit condition using our compressor isentropic efficiency. Then we know the nozzle turbine inlet condition. Turbine inlet temperature is given, turbine inlet pressure we can compute given the from the compressor exit pressure minus the pressure loss in the combustion chamber. So once that is done, we do work matching between turbine and compressor to find the turbine exit temperature, and after that we can use the turbine isentropic efficiency to find the turbine exit pressure. Okay, so once we know the turbine exit pressure, we can find out the turbine exit pressure divided by the ambient pressure. We get a pressure ratio, and then we compare it with the nozzle critical pressure ratio to see whether the nozzle is choked or not. Okay, so and depending on whether the nozzle is choked or not choked, the exit condition will change. Okay, so if the nozzle is not choked, we have seen how to compute the nozzle exit condition, the temperature and pressure. So if the nozzle is choked, we compute the pressure from the critical pressure ratio and the temperature from the critical temperature ratio, and once we know this is choked, we know the flow velocity will be equal to the speed of sound. Okay, so that is square root of gamma r times the local temperature, and then we can get the flow velocity at the exit of the nozzle. Okay, all right. So the next part is specific thrust. So here let's say we do specific thrust. So thrust is equal to m dot Cj times Cc, like exit velocity C5 minus Ca, plus here we will have the pressure thrust, because remember at the nozzle exit the pressure is higher than the ambient pressure, so we will also have the pressure thrust term here. So this is area of the nozzle times the pressure difference, which is P5 minus Pa. Okay, so we have to find out the specific thrust. So this is C5 minus Ca plus A nozzle by m dot A P5 minus Pa. Okay, so here we know all the quantities. C5 we know, C5 is known, we computed. Ca is known, the speed of aircraft speed or the flow to the inlet of the intake. We know P5, we know PA. We have to compute this term A nozzle by m dot. Okay, so here we are assuming that the air fuel ratio is very small, so m dot we can write is equal to density at the nozzle exit times the area at nozzle exit, right? It's better if I write this at A5, right? So the pressure thrust is generally equal to the nozzle exit area times the pressure difference, right? So we can write m dot as this. M dot is equal to density times area times the speed of the flow velocity, right? So what we need to find out is A5 by m dot. So A5 by m dot is equal to 1 by rho 5 into Ca. Okay, and rho 5 we can write in terms of the pressure and temperature. Okay, so rho is P5 by R T5 into C5. Okay, all right. So this will come out as 0.00557 meter square second per kg. Okay, all right. So now we also know this A5 by m dot air term. Okay, so now specific thrust is T by m dot A, that is C5 minus Ca plus A5 by m dot A P5 minus Pa. Okay, so here we know all the values, so we put it will come around 681 Newton second per kg. This is our specific thrust, so that is option B. Okay, is this clear? So here remember, so if the nozzle is choked, the pressure if the nozzle is choked nozzle, pressure thrust, so pressure thrust is this term A5 P5 minus Pa, that is not equal to 0. If the nozzle is unchoked, pressure thrust is equal to 0, since P5 is equal to Pa. Okay, so if the nozzle is unchoked, the exit pressure is equal to the ambient pressure, so that's why there is no pressure thrust. Okay, if the nozzle is choked, the exit pressure is equal to the critical pressure, which is greater than the ambient pressure, that's why we get a pressure thrust. Okay, so that's why what we see in the problem here. Okay, else if the nozzle is unchoked, your thrust is mass flow rate times the difference in velocity at the nozzle exit and the aircraft inlet. Okay, so I guess this is the last part of the question. So this is specific fuel consumption, SFC. So SFC is mass flow rate of fuel divided by thrust. Okay, or mass flow rate of fuel. So let's say I denote specific thrust here as Fs. Okay, so thrust is m dot A times Fs. So this becomes F fuel air ratio F divided by Fs. So F is our fuel air ratio, m dot F by m dot A. Okay, so fuel air ratio is given as 0.0194. The specific thrust is 681. Okay, so this you will get in kg per second Newton. Okay, so we want the answer in hours. Okay, so that's why we have to multiply it with this one with 0.0194681 into 3600. This is kg per hour Newton. Okay, so and the answer that we'll get finally is 0.012 kg per hour Newton, the option A. Okay, all right, so this brings us to the end of today's session. This went quite ahead of time. Okay, so if you guys have any questions, you can ask now related to today's session, and how, especially how the last problem was solved, which is related to the analysis of entire analysis of a turbojet engine cycle. Okay. If there are no questions, we can end today's session, and we'll meet again next Monday at 6 p.m. To discuss. Next day we'll discuss some problems on turbofan engines, afterburners, and other stuff, before some more thermodynamic analysis related to this aircraft engine cycles, and after that we will move on to turbo machinery, compressors and turbine, and their analysis. Okay. Okay. Okay, I hope this part is clear to all of you, and this will help you solve the last set of questions in the assignment. Okay. Okay, if there are no doubts, I will end the meeting. Thank you all for attending. Good night. Have a good week. Bye.